So before the program committee starts up with our speakers, we're going to ask the election committee to come up and share the announcement of the results.
All right, thank you. Okay, all right. So we just want to thank all of our candidates for participating and all of the members who voted. Really appreciate it. So now to the results. Don't leave it waiting. Okay, so our election results, we have our board candidates, Susan Forney and David Segal. What? Siegel. David Siegel. Sorry, David. We had a pretty close race, and we had 93% approval for our amendment updates, or our bylaw amendment updates. So thank you all for that. And all of this information is going to be available on the NANOG website going forward, so feel free to check it out. That's everything. Thank you everyone for your time. And that's the end of the results.
So we'll get started here. Our first speaker, before he comes up, I want to remind everyone, please fill out the survey. There's still a drawing at the end of the day for another, it's the Apple Watch, I think. So please fill out the survey. PC really values that feedback. And I'll remind you again and again of that. So our first speaker here is Faisal Iqbal. He's going to talk about data plane monitoring and segment routing networks.
Hey guys, so I'm Faisal Iqbal. I'm a software engineer for Cisco Systems, and I'm going to talk about data plane monitoring and segment routing networks. Unfortunately, Clay can't join me, so you'll have to live with me. So data plane monitoring, of course, is very near and dear to most of the operators. You want to make sure your network is functioning correctly, everything is going the way it should, there are no traffic black holes or other faults happening in the network. So for most of the slides, I'll just use this topology over here. So it's pretty simple. I'll be describing it, don't need to basically memorize it. So black holes occur when a router starts dropping traffic, and it could be that we are dropping, it could be for a single prefix, it could be just over a particular link, or it could be all the traffic over the network. And there are multiple reasons that it could occur. Sometimes there's a forwarding inconsistency where one of the network, let's say one of the line cards is a bit behind, it doesn't have the latest update. Sometimes the control planes of the two devices can get out of sync. And user can also, of course, can make a mistake, misconfigure, and that could lead to a black hole. So there are various causes. It's a significant pain point and something that we want to address in any decent OEM solution. So I'll just highlight this using a very simple example. So here we have a VPN, which a C device, C1, which wants to send traffic towards CE2 over the MPLS network. So in this case, it will send the packet to node 1. So node 1 will slap the transport label and the VPN label, and then send the packet towards next hop. So if you notice over here, the label, MPLS label that is being sent, it is unlabeled on the next hop. So, and this is not a very uncommon scenario in the network encounter. So in this case, it may just pop that label and just expose the VPN label prematurely and send it towards the next hop. And because, of course, the next hop is a core node, it does not understand the VPN label or the payload underneath it, so it's going to drop the traffic. And in MPLS networks, typically, it could also happen that you have ECMP in the network, and in this case, you may send the packet towards incorrect node, and that will lead to a black hole as well. With segment routing, the labels are global, which means that most of the network devices understand the labels. So even if the traffic is not sent to the correct node, it may still end up reaching the destination, but not through the expected path. It may take a path that is probably longer, or maybe introduce congestion in the network, or it may even break SLAs. So this is what I'm using as path divergence. So again, I'm going to highlight it using an example over here. So here, let's say we have a policy where we want to send the traffic from node 1 to node 7 through node 5. So in this case, we can have an MPLS label stack where the first label, 16,005, is the label to reach node 5. And then the next one is labeled to reach node 7. So node 1 builds this packet, send it toward the next hop, 3. So 3 is a penultimate hop. So it's supposed to pop the label and then send the traffic towards 5. But let's say there was an issue in 3. So instead of popping the label and sending it towards node 5, it instead sent it towards node 6. And because the packet still have 16,007, node 6 will pop the label, it understands it, and send it towards 7. So now the packet did reach the destination, but it is not taking the path that we expected it to take. And that can lead to congestion and other issues I mentioned above. So currently, there are various fault detection mechanisms available for operators. Broadly, we can categorize them as proactive, which means they are constantly scanning the network and making sure everything is working the way it should. But for large network, that gets really complicated because it's tough to proactively monitor the entire network very easily. So then operators have to also rely on reactive tools as well. So in reactive, you get alerted by a fault, and then you start use your arsenal of OEM tools to identify the fault and the point of failure so you can take a corrective action against it. And then we can also say that the tools available to you right now, they could be local, which means that they just rely on the node. They don't send any probes or anything outside the box. So for example, some routers and switches have a label or route consistency checkers, which make sure that label or routing database is in sync with FIB. But on the other hand, we have LSP ping or BFD. And these tools validate the entire LSP. So if something is broken, BFD can monitor it proactively at a very fast rate. And LSP ping it's not meant to be constant, very fast rate, but it can detect more faults and various other use cases as well. But overall, we can say that in this case, these tools are incomplete because they only identify a subset of faults. For example, BFD, LSP ping, they cannot detect path divergence because packets still reach the destination. So it will report everything is OK. And then there are also scalability challenges with it because you have high number of ECMP and ECMP combinations. So it just gets into an ECMP explosion. It's nearly impossible to monitor every single path end to end. So we think that we need a tool that can complement the existing tool set that can, well, we're not going to go away from end-to-end monitoring or local tools, but we can come up with something that complements them to monitor more fast that can remain otherwise undetected. And for this purpose, we are introducing segment routing data plane monitoring. So SRDPM is an independent solution that allows a node to test its entire forwarding path end-to-end in the sense that ingress to egress on the same device, not end-to-end in the network sense. For any MPLS traffic that could be received from any upstream towards any downstream ECMP. So in this case, we are not testing just one path. We're not just testing local probe and sending it out. We try to model the customer traffic exactly. And we do this through a distributed and localized detection mechanism that is based on source routing paradigm. So in this case, it can monitor the entire network. It can monitor the network proactively, constantly going on in the background, detecting any faults. And it's localized because we don't go beyond one hop. Each node just checks itself and then its immediate neighbors. It doesn't try to go beyond that because then we'll run into the same issues that we have with end-to-end tools. Instead, we can distribute the detection mechanism, detection over work to different devices in the network. So each device can just check itself and its neighbors, and you don't have to rely on just a single tool or one end-to-end mechanism. And because underneath, we use a specially crafted LSP ping packet. So LSP ping is widely supported by most vendors at MPLS level, and most operators probably who deploy MPLS, they use it every day. So you don't have to go to IETF, write a draft, standardize it, and hope that all your other vendors also support it. It's interoperable by design. And because we are relying on source routing, so in this case, source routing has adjacency set, which means that we can pin down exact interface or a link. So in this case, we can pin down the upstreams and downstreams, and using this, we can make sure that we test each upstream and downstream combination. Because you could have multiple line cards, and maybe if you test just one of them, it doesn't mean that the other line cards are functioning the way it should. So now I'll go into the mechanics of data plane monitoring, where I'll highlight how it works. So broadly, it's a two-stage process, or how we call it phases. So first, before the real work we want to do is we want to make sure that we are forwarding every prefix that can get from upstream towards the correct downstream node. But before doing that, we want to make sure that all our links are forwarding traffic correctly. It's not that let's say if one of the links is broken, then we'll see the same breakage across all prefixes, and we may think that it's an issue with the prefix when it's really a link issue. So we address this using adjacency validation. And once we have that one, then we'll also use it as a building block for our prefix validation phase. So here, adjacency validation, the basically idea is that you want to make sure that you are able to send and receive traffic correctly to each one of your neighbors. So here, let's assume that we have this topology again. So we are working on node 3. That is the only node that is running DPM. No other device in the network is running DPM right now. So in this case, it has links to neighbors 1, 2, 5, and 6. And right now, I'm showing only single links, but of course, you could have ECMP there as well on these nodes. So for each neighboring link, node 3 will construct an echo request packet that goes to the neighbor and then comes back on the same link. It will just transit through the neighbor. It will not get punted on the box. The box doesn't need to do the neighboring box doesn't need to do any software processing there. It will just simply switch the packet back to you. And then once we receive the packet, we can validate if we were the intent target. So in this case, for example, we have adjacency set label, first one, 24031, to take it from node 3 to 1. And then 24013 will bring it back from 1 to 3. So if we receive the packet back, because packet will have enough information encoded in it, we'll know that we are the intent target and we received it on the correct link. Let's say if packet end up on node 4, then we'll receive a fault. This link is not functioning correctly. And we can do this for the remaining links as well. So we did it for node 1. Now we can do the same thing for node 5 using its own adjacency set labels to and from, for node 6, and then node 2. So once we have that one, in this case, we know that all our links are functioning correctly. And again, I'm going to iterate that there's no software processing involved in the neighboring device. They're just going to switch the packet back to the DUT, in this case, node 3. Node 3 is the only one which is sending and receiving probes. So once we have that one, then we can identify if there's any malfunctioning link. So malfunction could be that maybe the link is dropping traffic. It could be that it is forwarding the traffic, either like the DUT or the neighboring device, it is sending it towards incorrect link or incorrect device entirely. So we can't use, if there's any malfunction, we can't use that particular link. We'll have to exclude it from our further validations. And also, we use this as a building block for the next phase, as you'll see. So prefix validation is what we really are interested in. We want to make sure that we are able to send and receive traffic from any upstream towards any of our downstream neighbor for that prefix set, and we want to do it for every prefix set in the network. And we achieve it by looping the traffic, because we want to simulate customer traffic path. We don't want to just generate a probe locally from RP, send it out over line card, because then customer traffic doesn't take that path. Customer traffic comes on an ingress line card and then goes out via the egress line card. And we want to model that customer traffic path. So we do this by looping the traffic using the adjacency seed label we just discussed. And then using this looping, we can actually get the packet back on the device. And then we have a prefixed label. Once we receive the packet, the next label will be prefixed label, which will take it towards one of the downstream devices. So now for any, let's say like we have a DUT3, we can identify the upstream link and the downstream link for any prefix set. And if one of them is malfunctioning, we can exclude it. So in this case, for any prefix set, we'll go through this process. So here we have for each upstream and downstream combination, the DUT, in this case, the device under test, node 3, it will build a packet, and plus echo request packet, because that's what we use for this one. That will go to our upstream neighbor, comes back to us, and then expires at an immediate downstream neighbor. And we can set the TTL to 3 to make sure. That way the packet doesn't go beyond one hop. We just go one hop up and then one hop down. And that way we are just limited in this one. We don't have to worry about the scalability challenges of end-to-end mechanisms. And then we have the prefixed label, because when the packet comes back at the DUT node 3, it will only have prefixed label. The adjacency labels would have been popped. So in a way, customer traffic as well will have the same label. So we are forwarding exactly like any customer traffic would. And because we could have multiple ECMP, here we have 2 ECMPs. So we want to make sure that we can test each one of them separately. So LSP ping has 127/8 destination addresses, and we can play around with the entropy to make sure that we can test each one of them correctly. And once we send it out to the correct downstream, we want to make sure that it reaches there. Let's say like if hardware and software are out of sync, we thought we were sending it towards node 5, but it ends up at node 6, we can't detect that scenario. So we include enough information in the echo request packet that we can do that. So we include the ID of the destination that we are trying to reach, and then the information about the label stack that should be expected at the next hop, the interface on which the next hop should receive the packet, and of course the next hop ID. So we send this packet out, it reaches the downstream device, and then downstream can make sure that it has a labeled path to reach the destination. Here our destination is 7. So node 5 can make sure that it has a path to reach the destination 7, and that path is labeled. And then it can also make sure that it was the intended destination. We didn't mean to send a packet to node 6, and it somehow ended up at node 5, and it was received on the correct link. And this information, along with the information of the next hop from node 5, is sent back towards 3 in an echo reply. So this is standard echo reply here. Node 3 is not running DPM. It's not even DPM aware. From its perspective, it just received an echo request packet, and it is just replying to that echo request. So it could be a non-Cisco box. It could be running an older version. That's the beauty of it. It's interoperable by design. So once we receive the reply, we can make sure, okay, if there was any fault, then we can alert the operator that for this particular combination, we are seeing an issue you may want to monitor. And we can also, I'll talk about remediation as well. That's also possible. And then we can go on to test the remaining combinations. So here for the same downstream 5, the traffic could potentially come from the other upstream as well. And similarly, we can test it for the downstream 6, both combinations, and then for remaining prefixes as well. So that way, we can test each upstream and downstream combination for any prefix set in the network. Right now, I've just described it for node 7. Okay, so as we saw, we are not going beyond one hop. So in this case, each node just takes the packet to upstream and then downstream, not beyond that one. So it will detect any forwarding because we are exercising entire forwarding chain at the DUT. So if there's any forwarding issue for a particular prefix set, we will detect that prefix that will detect that issue regardless of upstream or downstream neighbor that we have. And it can also detect most forwarding issues at our neighbors, at our downstream neighbors. For example, if downstream does not recognize that prefixed label, or it doesn't have a path onward, so it receives the packet with label, but it cannot send further with the label. It cannot send it unlabeled. We can detect that kind of scenarios as well. But if there's anything beyond 1 hop, so in this case, 7 or 8 or 4, they are not our immediate neighbors. So of course, we are not sending any probe to them, so we will not detect faults there. But DPM is meant to be deployed throughout. It's a distributed detection mechanism. So instead of deploying on a single node and trying to test entire network, instead you can offload the work to different devices. So you can deploy DPM at strategic nodes in the network to make sure you have a good coverage in the network. And of course, you want to make sure that operator gets a really good fault. It can operator get a fault notification message, and that notification message is informative and accurate. So when DPM detects a fault, it will alert operator. It could be through a message on the box, or it could be through telemetry mechanism. But it will notify it, and that notification will contain the information of the fault. It will include the links that are involved, the prefixed label, as well as a brief error description of what really went wrong. So you can take, and we can also have a remediation action, because once we know all this information, we have effectively isolated the fault in the device. We know what's going wrong with which prefix, what are the nodes, and what are the links involved in this one. And then based on the error description, we can know that, okay, what particular message, maybe it's an unlabeled packet. Maybe in this case, the next hop is not being sent correctly. Maybe one of the devices is running slow. So we can take a remediation action, let's say reroute the traffic, or reinstall the forwarding entry, etc. And then we will try to avoid fault as well. Okay, so far I have discussed this mechanism as a proactive, where it is constantly running in the background and then detecting faults. But we want to be flexible. We know that some operators, maybe they're running their own probes at a very high rate, and they don't want to run DPM very fast rate. Instead, they want to run it slowly over, but then based on certain network events, maybe they want to just test a particular prefix is installed correctly across all the line cards, across all the links. So you can test a single prefix, or you can test all prefixes. Or maybe you want to do it based on a certain network event, because typically faults don't occur in steady states. Maybe a link went down, some new link or device got added, so now you have forwarding updates, your IGP converged. It's gonna install a bunch of forwarding updates on the control plane to hardware path. And that's where, in this, when you're doing this installation, when you're installing these forwarding updates, that's where you can potentially cause issues, where it is gonna, if there's any bug, or maybe one of the line cards is slow, so it didn't get the updates, it's running stale version. Then when you have these kind of triggers, in this case, it could be a link going down, or an alert from IGP that it's converged. There's no further update for, let's say, a certain amount of time. Then you can run DPM to make sure that all the forwarding entries are installed correctly. It could even be a controller-driven trick. So we can let operator know that, okay, whenever they send a particular trigger, then we can monitor a set of, or all the prefixes in the network. Oh, my bad. So in conclusion, we believe that DPM is an innovative solution to data-driven consistency and identify any traffic black holes in the network. Instead of trying to do end-to-end fault detection or try to test all the possible combinations, instead we distribute the detection work through the devices in the network, where each node just tests itself and its immediate neighbors. And because we are using LSP ping, so it's interoperable by design. There's no standardization required. Your neighbors doesn't have to be running a particular version of the software or a particular vendor, etc. As long as they are able to send and receive echo replies and echo requests, they should be able to work. And we are not planning to, as I mentioned earlier, we're not intending to replace existing tool set that you have in your arsenal. They have their own place, they're really suitable. We are not trying to be BFD. We're not trying to be LSP ping or discovering all the possible paths in the network, et cetera. Instead, we believe this tool complements the existing solutions that operators may have, and then instead of replacing them. And of course, it is ready for adoption by customers. We are working very closely with some of the customers. So in this case, Bell has joined us as the co-author of this talk. And if you have any question, I'll be very happy to answer these questions. I guess that's it.
Andrei Kostin, Tixavi. Have you done any scalability testing for this solution?
Yeah, of course. So scalability is very important. The thing is, you could have some networks maybe running few hundred or even less than 100. Other could be running thousands of prefixes. So yes, scalability is an important concern, and we have various tuning parameters because in the end, we want the solution to be flexible. So in this case, you may want to have a solution where you can tune the detection interval, you can tune the packets per second that we are sending with. So using these tuning parameters, we plan to cover up to several thousand of prefixes. We can discuss separately, but I can give you the numbers on that one. And of course, for each one of them, we can have a high number of ECMP as well, upstream as well as downstream.
Okay, thank you.
Okay, I guess you guys have 5 minutes before the next one. So, all right, thanks, guys.
Thank you, Faisal. I'm going to introduce our next speakers. We have 2 of them, Ian Flint and Varun Varma, coming up. They're going to talk about Panoptes, which is a network telemetry platform.
Hi there. My name's Ian Flint. This is Varun Varma, and we work at Oath, a company formerly known as Yahoo and AOL and Edgecast. So we were all combined as part of the acquisition of Yahoo by Verizon. And I run network automation. One of the big challenges that I faced when I came onto the team was the proliferation of point solutions for doing monitoring of devices. And so we had a whole bunch of them. We have a significant MRTG footprint that's hitting our devices. We have a custom SNMP poller called YWatch that's hitting our devices. We have a point solution around load balancers, just all of these systems that had grown up organically over the years, and the systems that depended on them that had also grown up around them. And so one of the challenges that we undertook to solve was to take those and consolidate them into a single polling platform, universal polling and metrics distribution platform, which we called Panoptes. That's what we're going to be talking about today. So,
hi, my name is Varun. I'm the lead engineer for Panoptes. And as Ian had mentioned, so essentially we built Panoptes as a Python-based network telemetry platform. There are 3 distinct components that Panoptes has. There's discovery, polling, and enrichment. And we'll be talking about some of these details during this talk. Here is an overview architecture diagram of what Panoptes looks like. So it's based on some supporting services. There is Celery, which is a very popular Python distributed job management system. There's Redis, which is an extremely fast in-memory key-value data store. There's Zookeeper that provides distributed locking and leader election services like that. And then, of course, there's Kafka, which we use as a message bus. On top of all of this, we actually built a plugin framework, and I'll go into some of the details later. Now, we implement 3 types of plugins, discovery, polling, enrichment. And then on top of this entire framework or the stack, we implement device-specific plugins. Currently, we have plugins that use SNMP and APIs to actually collect telemetry data. There's a bunch of supporting services in addition to the core platform, because obviously after we collect this entire data, we have to store this and analyze it. So we have a time series database that we use. We have an internal CMDB that we use for device discovery. And then we use Chef for deployment and configuration. I'm going to go through some of the core concepts that Panoptes as a platform has. So the very first concept is this notion of plugins. And this is where Panoptes is actually fundamentally different from a lot of SNMP-based polling solutions. So what a plugin is essentially an implementation of a well-defined Python interface class. So you can essentially, because it's Python code, you can actually write code to collect from any source that you like. It could be SNMP, could be API, CLI, or anything else that might come up in the future. As I'd mentioned, there are 3 types of plugins: discovery, enrichment, and metric plugins. Another core concept in Panoptes is this notion of resources. So what a resource is it's essentially an abstraction of what should be monitored. In the most common case, a device or a network device or a host is a resource. But a resource could be an external API endpoint. There's metadata associated with resources. Another interesting thing in Panoptes is that we've come up with a DSL which actually mirrors or is quite close to SQL, which lets you actually select resources. You can see an example of the DSL on the screen, where we're saying, okay, I want you to apply certain type of polling only to devices which match this criteria. Now, typically, these types of DSLs are available within time series databases on analytic tools. But here, the difference is that we actually have made it available even at the time of deciding what to poll and how to poll it. Another concept is metrics, which obviously is one of the core things. A metric is anything that can be measured. So it's essentially always a number. Metrics typically tend to be fast changing. While that might sound obvious, I'm going to contrast it with something called enrichments later on. And like I said, because of the plugin architecture, metrics can actually be collected through any mechanism. Okay? Another concept that we have introduced is the notion of enrichments. Now, what enrichments are things that are not numbers. They could be numbers, but essentially these are things which are not that frequently changing. A perfect example would be when we're collecting telemetry data for interface metrics, right? So the interface counters are metrics, but the interface name is actually an enrichment that we apply. And the thing is, and enrichments might not necessarily just come from the device that's being monitored, it might come from external systems. One example is when we poll a device for, say, BGP sessions, we get back ASN numbers. Now, we might be interested in reporting the actual peer name, not just the ASN number. And that's where, that's not something we can query from the device itself. So that's again a place where the enrichment framework comes in, where we can query and enhance the data that we've collected from the device by using external lookups. Also, because metrics are typically not numbers, they're typically strings, they tend to be more expensive to process than metrics. And that's one of the reasons there's transformation and lookups needed. Case in point, for example, I mentioned the ASN number to name lookup. It's not something you want to do on every poll cycle. It's also something that, because they're expensive, we tend to cache them. Again, an example is interface names, interface aliases, things like this, which we don't actually need to collect in every poll cycle. Overall, what this does is, by being able to divide metrics and enrichments, is it actually lets us scale a lot, because we don't have to collect the complete set of data on every poll cycle. Now, a word about the data encoding and distribution. Panoptes was built from day one as a distributed system. We knew that at our scale, building a system which could only scale vertically, which means we had to add more processors or more memory to the same host, would simply not work. So we've actually built it as a horizontally scalable system. And there are two dimensions to that. One is the fact that the three subsystems that I mentioned, discovery, enrichment, and polling, are completely decoupled, which means we can scale them out individually. It also means that within each of these systems, we can actually spin up more hosts. And for example, if I need more polling capacity, I can simply spin up more hosts, and it becomes part of a cluster, and I get more polling capacity. Because these systems are, because it's a distributed system, we obviously need a way to pass data between them. We use Kafka and Redis, depending on different use cases, to actually pass data between these subsystems. The other thing is, again, because we're passing data, we need to choose a serialization format. So we decided to go with JSON. Now, JSON is extremely inefficient and it's slow, but then it is actually very operator and developer friendly. So it's a cost we were willing to pay. This is what the overall workflow for this looks like. So, obviously it begins by us collecting data. There is some post-processing support that we have. We call these transformations. An example of a transformation is that when we collect raw counters from a device, sometimes it's not meaningful to send it as is downstream, so we can actually convert them into gauges. And then once we do the post-processing, we place the data on the message bus, and then we have different consumers. Here are two workflows that I've shown. There's one workflow that takes the data and puts it in a time series database, which we actually use for graphing, alerting, and our internal time series database actually also stores the data on our internal grid, which we use for analytics and reporting. At the same time, there are use cases where we need the most recent data, not necessarily the historical data. So we actually have a consumer which stores this data in MySQL and exposes this through an API. And then we built UIs and CLIs based on top of those APIs, and I'll be showing an example of what that looks like. So given that we serve 1 billion plus customers, obviously we have a very large footprint. And there are a lot of things that we learned while operating this. First, let's talk about what the scale we're operating at is. Now, this is an indication of orders of magnitude. These are not absolute numbers. So we have hundreds of thousands of servers. We have tens of thousands of network devices. We have millions of time series. We do collect data every 60 seconds, which is actually faster than typically what we were doing with MRTG of every 5 minutes. Now, some of the scaling issues we faced. I mentioned earlier that Panoptis was designed to be horizontally scalable, and this was intentional. We paid a lot of upfront development cost to do this because, frankly, this is not easy to bolt on. Scalability is not a feature. It's a design principle, so you kind of have to take care of it while designing the system. We decided to go with Python. It is extremely slow, extremely inefficient, something we were prepared for, and it turned out to be true. What we have done is there are some high throughput actions, like specifically the actual SNMP protocol interactions, we've delegated to C extension modules so that we can actually get performance. And then again, at our scale, we broke everything. All the default installs for Redis, Zookeeper, Kafka, they would just fall over because we would hit all the default limits. So there's a lot of tuning we had to do for each of these systems. The other aspect for scaling was with data this large, we did not want to build a centralized system, both for performance and availability reasons. So the way we did this instead was that we have these local deployments in each of our data centers. And what we do is these data centers collect data for their, obviously, all the network devices within the data center, but also collect devices for nearby regional sites. At the same time, we don't want discovery of data to be problematic. So somebody using an API should not have to figure out where they can get this data. So what we did was we came up with a federated API structure where what we do is between all these data centers, we actually cross-populate the metadata. So each data center does not have all the data, but it knows where to get all the data. So you can make a query and say, okay, I'm interested in data about device X. And you might get a response saying, here's the data. Or you might get a response saying, okay, I don't have the data, but I know who does, so why don't you go ask that person? And this design has helped us both with scalability and fault tolerance. The plugins that we have already written, we have support for Arista, Cisco Juniper metrics, we have system metrics, we have something we called functional metrics, which is go beyond just the CPU memory, and they're very, very device and platform specific, and more importantly, they're usage specific. So if you're using an A10 load balancer for load balancing, we have different functional metrics versus when we use it for large scale NATs. What we've also done is, because this is a platform for telemetry collection, we've actually also built state and topology collection for Cisco devices. This is something we're looking at actually integrating back into our discovery so that we don't only figure out what devices to monitor through our CMDB, but through an actual walk of the network. Some operational experiences that we've had, and anybody who's worked with network telemetry, I'm sure would have seen these. We had a lot of inconsistencies between metrics which were reported from different platforms and different OS versions of the same platform. And frankly, in terms of development, this was our single biggest time drain. SNMP, it is really old. I believe the SNMP v2 specification came out 21 years ago. So it is old, but it is ubiquitous. As much as we'd like to be able to use API and streaming telemetry, there just simply are many cases where a lot of telemetry data is not exposed through those. So, it's something we have to live with. API performance tends to be much better than SNMP. Again, anybody who's done telemetry would know this. The other thing is, when we were building this, we had some use cases. Like Ian had mentioned that there was a whole class of services or systems that we had, and we knew what we wanted to replace. But we also knew we didn't know how this data would be used. And that's where, for example, using Kafka proved to be the right choice. We already have 3 types of downstream consumers which transform the data and send it to different systems. And this is a much better approach than trying to collect data, the same data in different ways so different downstream systems can consume it. I'm sorry, I think the slide's been repeated. Oh, sorry, I'm going back. One interesting thing is, one thing we were very careful about is, even though we place all our data on Kafka, we do not integrate those raw streams with third-party systems. Now, this might sound counterintuitive because one of the big advantages of using Kafka is there are so many consumers that you should be able to hook in any consumer and get the data. But here's the problem. If you do that, you can never upgrade. Because the problem you will have is you'll be tied into a certain Kafka version because there's a downstream consumer that depends on that Kafka version, or you'll be tied into a specific serialization format, whatever you were exposing on sending or serializing on Kafka. If you ever change that, your downstream consumers will break. What we do instead is that we actually take this data and we store it in a transient MySQL database and expose APIs. And I'm going to show an example of the APIs we have. And the advantage that has is it completely decouples my system. We can change the internal serialization. Heck, we can even get rid of Kafka for something else that comes along without our external contracts changing. We built custom UIs again, I'll show a couple of examples of what that looks like. These are examples of APIs that we have. On the left, you would see this is a very purpose-specific API that we've built to get data for whips from load balancers. At the same time, and this tends to be very easy to use and performant. We also only expose the last data point through the API. We also have a API which actually exposes historical data, and you can do ad hoc queries on it. This is actually an open TSTB API. So this is not something we've built. Internally, we use open TSTB. Tends to be slower, but then you can run aggregations and you can get historical data. One of the things I mentioned in the architecture slide is that we have a time series database. So we actually have an in-house time series database and visualization solutions, which Ian actually had architected. It's based on OpenTSDB with a lot of, obviously, performance optimizations, a lot of other improvements. This is an example of a dashboard that we've built based on our internal TSDB and the internal UI that we have. Now, because it's a centralized TSDB, our team doesn't have to manage it. It's managed by a central team for the whole of Oath, and there's economies of scale and operations are simpler. Here's an example of a couple of custom UIs that we've built. The left-hand side is actually a device dashboard. The right-hand side is actually a WIP dashboard. Now, these have been built using the purpose-specific APIs that I had shown. And because they only expose the last point-in-time data, they tend to be performant, so our UIs are actually quite responsive. Looking forward, one of the next things that we want to work on is actually streaming telemetry. We have a framework in mind where we use a streaming telemetry collection. GNMI is the leading contender. But we also reuse the infrastructure that as we have. For example, in the GNMI case, we do need to create outbound connections to actually get streaming telemetry from them. And for that, you need an authoritative source of devices or resources to connect to. That's something Panoptes has. Similarly, for GNMI, you would want to, the raw metrics or telemetry data that you get over streaming, you will again want to enrich them. Examples of enrichment, I gave the ASN example, but there's another example. For example, the geolocation, the physical geolocation of the device is not necessarily something that you can figure out from the device itself. So these are external enrichments that we can apply to the raw metrics that we collect. Now, we've actually spoken and presented a lot of this at NANOG 70. So the big thing, though, is the stuff that we've done after that. When we presented it at NANOG 70, we had discovery and polling. We did not have enrichment. What that meant was that on every poll cycle, we would actually be getting all the static information again, which had scalability problems both for the platform as well as for the network devices. By adding an enrichment subsystem, we have alleviated those concerns. We have implemented we actually have implemented a whole bunch of plugins to give us full coverage or close to full coverage with a network which is a multi-generational, multi-vendor network like ours. We worked out scaling issues. Obviously, that required a lot of platform changes and tuning and things like that. But most importantly, what we wanted to talk to you about is that today we are actually announcing the open sourcing of Panoptes. We are releasing an MVP. We're open sourcing the core platform that includes the 3 subsystems that I've been talking about. We are open sourcing interface metrics and enrichment plugins. This is a very small subset of the plugins we have, but in the spirit of releasing an MVP, this is what we'll be going to market with. And we're also introducing an integration with InfluxDB as a time series database. So this is an example of an InfluxDB dashboard that you can create if you actually use the open source time series, the open source implementation that Panoptes has. And you can actually go get it at this URL. Any questions?
Hi, Tony Tauber, Comcast. It looks like very good stuff, and set up the way I would think too. Also, with the enrichment cache, do you actually put the enrichment data in with the? You wouldn't put it in the time series. I mean, it wouldn't sit on the side and you join it when you need it or something.
Okay, so the stitching happens actually at the time of polling. The polling plugin can actually choose to go out and get data from the device or actually use the data from the cache. So, but what happens is when the polling plugin is done, what comes out of this is a consistent model. Actually, I forgot, I didn't really touch upon that. We actually have well-defined internal models for everything. So, for example, taking the example of interfaces, when we collect interface metrics, no matter what platform, what version, what we're collecting interface metrics from, every plugin must produce interface metrics which has a certain set of metrics and a certain set of dimensions or tags. And those dimensions or tags could either come from the device or come from the enrichment cache. Does that make sense?
Okay, but I mean, it seems like extra if you're storing at every metric timestamp, all this metadata in the same place, that's kind of redundant because it's always the same or the same for days on end. Or
that is true, but most time series databases actually optimize that.
Oh yeah, right. Okay.
Yeah,
so they do it.
So
Okay.
we count on essentially that. Yes.
Okay.
Well, and oftentimes the enrichments change over time as well.
Right,
So-
they do.
So you do want to store it with the source data so that if you do aggregations based on those, that you get an accurate answer.
Yeah. Okay. Yeah, that's a good point. Makes sense. Thanks.
Hi, Aditya from Arista. Quick question on how granular is the timestamps on the time series graph? Is it millisecond granularity, 1 second?
We are collecting, so plugins, okay, because it's polling, it's not going to be accurate. Yeah. It is going to be the time when the data made it to the polling collection system. The plugin is configurable. There's a parameter called execute frequency, so as frequently as you wanted to collect the data. Currently in our production system, we have set it to collect to every 60 seconds. Okay. We could go down more for some devices, Arista devices, sure, but some of the other platforms, they just won't be able to handle the SNMP load.
Okay, thank you.
Which is why streaming telemetry has to come in.
I believe our backend supports 1 second resolution.
Yes.
But we poll currently at 60 second.
Also, just an implementation detail, the timestamp resolution is millisecond. Yeah, that's what the platform is capable of. Any other questions? Thanks, guys. Bye.
Thank you, Ian and Varun. It's a good talk. Take that. And before the next session here, we're going to have lightning talks, 3 brief talks. Before that, I want to remind everyone, last chance, please fill out the survey. We will do the final drawing, I think, in about 30 minutes. So please fill it out if you haven't already. That being said, our first lightning talk is going to be Brian Jeems. He's going to talk about PTP demands on the campus.
I'm Brian Jeems. I'm the network manager at the University of Idaho, and I wanted to talk about precision time protocol and the changes that's made for us in our campus network.
really, we had no idea we were getting into precision time protocol 2 years ago. We just got a simple email request that, hey, we got this Dante-enabled classroom audio equipment we want to start installing. We need a dedicated VLAN. It needs to be a VLAN extended between 5 different buildings on campus. So that's pretty easy. Lesson 1 that we found out right away, hey, this doesn't work as expected if we don't have multicast. It needs IP multicast to work. So we had solved that for some other AV solutions. So add IGMP querier, PIM sparse mode. Seemed like things were good for a few months. Then, hey, we got major problems. Classrooms audio is cutting out all the time. And we're looking, we have packet loss. Is there some kind of network problem of a more typical variety? But turns out, no, it's the Dante protocol is going into election mode over and over again. Because if there can be only one. It's Highlander in the Dante world. There must be one master clock on this VLAN between multiple buildings. And so, here on the left is a happy microphone that's got latency below 2 milliseconds. On the right is an unhappy microphone that's seeing occasionally 5 millisecond latency. That'll cause it to kick off the election process. And the reason that's cutting out audio is that the microphones mute when they're doing the election. So it's going off all the time. What did we do about that? Well, quick and dirty solution. We have to solve this problem right now. We segment. So we pull the VLAN off the building trunks. You lose management ability, but the microphones are just fine working in with link local addresses, and every building has its own master clock. Everything's fine. We do a little more elegant version of that with a VLAN ACL, a few weeks later after we studied the situation. And really all we needed to do was block the P2P traffic in the core so that the buildings didn't see each other. And so each building could elect its own clock master. But now our classroom technology team's not happy because audio doesn't work between buildings. They were using that for monitoring. They didn't have any strong driver for it, but to monitor quality, to do troubleshooting, and for future needs to be able to have it classroom sessions and audio into multiple buildings on campus. They wanted that to work. So we got busy. We kind of put it on hold until this summer and fall, and started working on the real solution. And for me and for my team, this was something brand new. I was talking with an engineer who had spent a good part of his career Monday at lunch in a wireless carrier network, and to him this was obvious. Hey, if you're doing P2P, you've got to have QoS. So we figured that out eventually, and so we just did in general, we've tried to keep the network real simple to operate, but we've added now QoS on the uplinks for any of the buildings with the Dante network. We're not quite there. We'll get there by the end of the month in terms of, right now we're down to 2 master clocks. There's one building that we haven't added QoS to that we've got to do a switch upgrade on. But then we'll be with everything running on one master clock with the full functionality the classroom technology team wanted. And just one more comment on the alternatives. A lot of the vendors, there's all kinds of AV vendors offering Dante equipment, and they recommend things like, oh, just build a separate network, totally separate switch infrastructure. Being a university, we like to be a lot more frugal than that, so that wasn't an option for us. And also, we could have made Dante subnets, one subnet per building, just kept it a layer 3 segmentation. The downside with that is then you want to do inter-building audio. Hey, here's some really expensive software you can buy that'll make that happen between subnets. Again, we wanted to go for the lower cost option than that and just keep it one flat VLAN around campus.
And I just provided the Audinate reference link that has some of their reference details about this. So that's our story about P2P on the campus network.
Thank you, Brian. Our next lightning talk is going to be Alejandro Acosta. He's going to talk about V6 open resolvers.
Hello, well, good afternoon. Well, my name is Alejandro Acosta. I'm going to talk to you about a project that in LACNIC we feel something like proud about this. Basically, it's identifying DNS open resolvers, as you can see in the title, which is quite specific. Well, as all of you know, to identify DNS open resolvers in the IPv4 world is quite easy because the IPv4 address space is not that big. In IPv6, it is more difficult, and we needed to take a different path. So, what we did? Basically, we are taking, with a very specific TCP-DOM command, we're creating a pickup file in a root server. Actually, this is a reverse DNS root server. It is not the root server that traditionally we listen, but it is somehow a server that receives a lot of queries. The queries that are getting that we can identify in step 1, we can safely assume that are recursive servers in the internet. So what are we doing after that? After we have the pickup file, we process it, we work with it. We are using PyChark to do this. We remove somehow duplicates and IPv6 addresses, and so on. Then, after we have the IPv6 address identified, which we know that it is a recursive DNS server, we perform a very simple query trying to see if that IPv6 address allows recursion. Okay? This is actually the way that we identify IPv6 addresses. I am doing some emphasis here because traditionally when we present and we show this project, the main question that we receive is how do you identify the IPv6 address? There are many other ways of doing this. And well, finally, the last step, of course, is processing the data, showing results, publishing, and so on. I'm going to skip this slide since the results, I'm going to show most of this. OK, there is a summary. Maybe this slide is interesting. You can see by RIR the total of IPv6 DNS server that we have identified. For ARIN, let's talk only about the first line. We have identified almost 2,000 IPv6 DNS servers. What we did, we ran a simple query to all of them, and we were able to get 51 open resolvers. Okay, as all of you know, maybe this is not the expected behavior most of the time. Open resolvers are not good in internet. Of course, we know that some providers in somehow have DNS recursion enabled to everybody, like Google and many more. So what else? This is more or less the same information that that was shown in the table. Let's talk one more time about ARIN, since we're in ARIN region. In the most left bar chart, you can see in the blue line the total number of servers that we have found, and the orange line more or less shows the DNS that were open in somehow. Okay, it is allowed recursion. This graph, it is only for LACNIC region. Sorry for that. I did this slide last night. Since we are getting data since March of this year, we were able to create a timetable. However, we can do this for any RIR and for any country, actually, that we wish. Basically, you can see that on the first graph, the amount of open DNS resolvers, IPv6, that we have found in our region, in LACNIC. And in the second graph, you can see the evolution of the non-open DNS servers that we have found. Later, you can see that Brazil, they have the most amount of DNS servers, and the same case for open resolvers in IPv6. And we have found something that is interesting, at least from my point of view. We have identified that certain /64 prefixes, there are a lot of resolvers in each. For example, in the first line, we found 62 servers in only one /64 IPv6 prefix. We believe that this is because of the privacy addressing that some operating systems have implemented. But this is, from my point of view, this is quite interesting too. What were we looking for? This is type of results that we have. You can see at least yesterday I did this, a couple of ARIN results from Canada and from the US. I only took servers that we were able to find that were closed. On the very right, just on the left of ARIN, we were able to get the owner ID of that IPv6 address. So after that, we're able to contact the owner of that IPv6 address and tell him or tell them, sir, you have an IPv6 open resolver, please take care of that. And this is an example of what LACNIC members, only LACNIC members, are receiving in this moment. This is an email that we started sending about 6 weeks ago. You can see that every Monday, you can see something like, dear member name, you appear to be running a DNS open recursive resolver at IP address, blah, 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 blah. It explains what it is. There are 2 examples in how to fix this for bind and unbound. And I'm happy to tell you that we have already got evidence of people that receive our email and fix their server. Actually, we have a very nice example. Last week, one member of LACNIC received the previous email. He had 2 servers. Of course, we only found one of them, and the member fixed the 2 servers that they have. So it is a very interesting example that now we were able to do this, and we are very happy. We are not sending the email to other regions, for RIPE, Afrinic, or any other one. If you wish to contact us in somehow to go in detail how we are doing this, please feel free to contact me. Our next steps is integration with some LACNIC systems, when the user enters username and password, automation of some statistics, publishing open data. And something that we think could be quite interesting is trying to find out if some of the DNS servers that we were able to find probably are in squat prefixes, prefixes that has not been assigned by any RIR or IANA even. And that's all what I have. I don't know if there are time for questions. Oh, hello.
Good? Okay. Wes George with ByteGrid. I'm curious, did you see any 64 addresses in the analysis you did?
64 addresses? You mean map ID addresses?
Like 2002::/16.
Ooh, actually, that's a terrific question. Unfortunately, I did not pay attention to that, but I still have the data.
So
I'm going to do it now that you mentioned that.
I might suggest that you look at that because I was analyzing earlier this year, I was analyzing a V6 DNS dictionary attack for a large DNS provider. And out of, let's see, out of the 400 or so open resolvers that I found out of the list of querying hosts that were participating in that dictionary attack, more than half of them were from 6-4 space. And I couldn't really determine whether that was some sort of weird vagary where, because there was a 6-4 functional address, the DNS server was just doing that because it was configured and it was using whatever available interfaces, or if there was some sort of an explicit effort there, or if this was more, the two were unrelated. Like you had a v4 open resolver that also had a 6-4 address and was talking via that interface. But there's probably some analysis to be done there, because one of the questions that might come out of this is it time to just start configuring authoritative and recursive DNS servers to reject queries from 2002::/16 as sort of overtaken by events and no longer useful, and thus just closing down an attack vector? I don't really have a good answer to that, but that's the question raised in my analysis.
Well, terrific, interesting. Believe me, I'm going to my computer and I will try to find the list of IPv6 addresses regarding that 6-4 transition mechanism.
And if you want to see the data on mine, it's if you go to iepg.org, it's in the March 2018 presentations.
Okay, let's talk about that later. Thank you. Bye.
Thank you. Thank you, Alejandro. Thank you. So our final lightning talk speaker. Thank you for doing that. Yeah, that's right. It's going to be Ignas Bagdonas. He's going to talk about the end of VXLAN, or sunsetting.
Hello there. So for the end of the event, let's discuss one topic which has been quite much beaten over the 3 days, VXLAN, and what is happening with that. So a small note to other fellow presenters. Please be careful with your spelling. That abbreviation is all 4 capital letters, not in other way. So the history of VXLAN. It was a successful accident, in fact. Around a decade ago, one particular vendor was working on a particular family of the products, and they had some set of requirements to be able to carry Ethernet frames over IP transport. So it was designed with certain tradebacks, knowing that this is not a universally applicable solution. It was not part of the IETF working group process. Eventually, it came to the IETF as an individual submission and was mostly there for documentation purposes. It actually took the world by surprise. It was simple enough, and to this day, it is the most popular encapsulator for carrying general layer 2 payload over IP. However, that encapsulator is starting to show off its limitations. And the limitations are 3 large families. One thing is there's no possibility to indicate the type of the payload. Whatever gets into the tunnel at the other end is received as is without any indication. There is no way to indicate that the packet which is being sent is not the actual client packet, but something else. And the worst of those, which would be able to solve those 2 problems, is that there is no extensibility in the protocol itself. So the protocol identifier. It is assumed that what is carried over VXLAN tunnel is an Ethernet payload. And if you need to have a further demultiplexing, you need to carry the protocol identifier in the payload Ethernet address, or use some other internal encapsulator within that in order to be able to demultiplex that. Certainly that can work. That's not the easiest or say the most flexible way to do that. Now, one possible solution which is used in practice is to run parallel tunnels. That certainly works, and the namespace for the VNI identifiers is sufficiently large enough. However, there is another practical problem. The cost of the tunnel itself as an entity on the element is far bigger, and that is a far bigger practical problem than the perceived depletion of the VNI identifiers. Non-client payload. There's no ability to send out a packet, a frame, which does not belong to the client, and consequently, there's no ability at the other end for the client to distinguish that this packet is actually not a client packet, but something else. And this basically rules out a majority of the traditional OAM mechanisms which we are familiar with. For example, running BFD over VXLAN tunnel is definitely non-trivial. There are workarounds of doing that, but if we want to compare that to equivalent of the MPLS equivalent solutions, that's just nowhere near. And all sorts of OAM and non-client payloads, they assume that the client is aware of that and cooperates. So if you have a scenario where you want to validate the liveness of VXLAN tunnel, this assumes that the client itself needs to be aware of that BFD session. It's not necessary enough to terminate a BFD session only on the network element itself. VXLAN is not extensible. All of the fields, all of the values in the fields, they are predefined, and if we are talking about the interoperable extensibility, it is just not possible. This results in various proprietary extensions. Yes, such things do exist, and we certainly cannot talk about multi-vendor interoperability in this environment. It was becoming evident that such type of encapsulators, they are popular, they are solving practical problems, and therefore industry overall needs a more flexible and interoperable solution. IETF started a dedicated working group, Network Virtualization Overlays over Layer 3, around 2012 timeframe. And the major requirements put up front that group were to develop an similar or equivalent encapsulator which had the extensibility, multi-vendor extensibility, which would be hardware friendly. Again, we are talking not only about the software implementations, which are easy, but we are talking about the hardware-only implementations for which variable length structures and all sorts of field manipulation are really costly. There were concerns being raised about the lack or the complete lack of security aspects in VXLAN, and also ability to implement that in practical terms by the majority of the vendors, not only a selected few. And what resulted? There were a multitude of proposals. Three main ones: Genève, this is actually not an abbreviation, this is the name of a protocol. GUE, generic UDP encapsulation, and direct and semi-backwards compatible extension to VXLAN, the VXLAN generic protocol extensions. GUE was perceived to be too complex. It's a flexible one. It provides a lot of functionality, but to implement that all in hardware was seen to be too complex. And the backwards compatibility nature of GPE was seen to be too limiting for this protocol to be future-proof. There were some niche protocols and proposals. They did not advance too far. So Genève was seen as a compromise between the extensibility and the ability to implement that in, well, practical systems. So today, if we are looking from an IETF perspective, the direct successor to the VXLAN is Genève. What that protocol is and what it does, it's an extensible encapsulator able to carry different types of payload even at the same tunnel. It has ability to signal that some payload being carried does not belong to the actual client. This is a service payload. It has ability to do integrity check on the header itself. This is to limit out the possible attacks of injecting stray Genève packets into the network. It has ability to encrypt the payload if that is considered to be needed. And it allows roughly for 250 bytes of vendor extensibility space, and does that in a manner which is interoperable with, among the vendors. It simply uses the vendor's PCI identifier to indicate vendor-specific extensions. It looks like VXLAN is just a better VXLAN. So what is important if you are designing a new, especially new environment which uses these types of encapsulators? If OEM and interoperability is important, VXLAN is just not an option. This doesn't mean that VXLAN is completely unusable and broken. If you are in a single vendor environment and you are happy with rather limited ability of OEM tools, that's definitely fine. If you are looking into something more complex and more future-proof, Genève is the right way to continue. The current state of the industry is that majority of the relevant component vendors do have either shipping or sampling support of Genève in their products. System vendors are getting there. It's some are in trials, some are in prototypes. And what is mostly now needed and required from the community is to start looking from a design perspective. If you are looking into the overlay type of designs, seriously consider VXLAN as being obsolete. This is only about the data plane. No changes in the control plane, so your favorite EVPN or whatnot you are using stays exactly the same. The only change is that the encapsulator used for tunneling your payload is now different. That's it from my side. Thank you.
We have time for a question or two, if you have it. Otherwise, thank you, Ignas.
Right, thank you.
So before we close, first, on behalf of the program committee, I want to say thank you to all of our speakers. I think we had a pretty good week so far. And I want to announce the final survey drawing winner. Andre Kosten, or Costine? Thank you. I'm always glad when the winner's here, because otherwise we have to figure out backups. So, and with that, I'm going to turn it over to our Executive Director, Edward. Thank you, Edward. There you go.
Just so I stay on course. So first of all, I want to talk about the election results. So as kind of a recap, the amendments for 2018, the updates were approved. We have retiring board members of Ryan Donnelly and Dave Timken. And I'd like everyone to kind of give a round of applause for their service to our community. I know personally they were very, very important to my onboarding process, and I appreciate the support they've given me as I've been on NANOG as Executive Director. We have new board members, which are Susan Forney and also David Siegel. We have a new, they didn't put in the information, so I'll just tell you. We have a new chair, that's Sean Kennedy. Our new vice chair is Tina Morris. And our new treasurer, our existing treasurer will continue. Will Chernock will stay in that role. And then finally, Susan will be joining us as treasurer. Secretary, sorry, thank you, secretary. Will's treasurer. And I'd like to take a minute and talk about membership. For me, as executive director of NANOG, if I had kind of one thing that's kind of my thrust, that North Star that I try to focus on, and that's really thinking about the future of NANOG. I want NANOG to be around so that if my grandchildren decided they wanted to be members of NANOG, it would exist and it would be relevant. So my thrust is that. And I actually call upon members and non-members alike that being part of NANOG is about seeing the future of NANOG, seeing something that exists beyond us, something that will outlive us, and something that will be a strong contribution to our community and the world beyond. In a modern society, the internet is the very foundation. There are entities that exist now that never existed before prior to the conception of the internet. And I believe that all of you here are part of the keepers of that, who make that happen and make that a reality. And your participation within NANOG is critical to assuring that these kids here may someday become members of NANOG and that it exists and it's relevant for them. Now, the other kind of converse to that, which I think is most dangerous, is indecision. If we sit back and we expect someone else to take the front, we expect someone else to take the lead, someone else to make a difference, then we are going to become victims to indecision. And indecision is never good. I had an old boss who always used to say to me that indecision is a decision in and of itself. That saying, why did I think someone should become an active member? You help us deliver meaningful content to the community. You help us govern NANOG in a reasonable and responsible manner. You help us create a sustainable community of inclusion and diversity. And finally, you help us to build an organization that will outlive all of us. Now I'll get into the customary meeting stats. So we had 940 attendees at the meeting. Member registration was 249, students 9, speakers we had 20, college immersion 21, female attendance 12%, and countries in attendance 21. Our top organizations, NTT, Oracle, Cisco, Microsoft, Aaron, and Nokia. Organizational demographics, service providers made up 40%, vendors 21%, data centers 10%, IX network operators are 12%, nonprofits 10%, and others make up 7%. Special thanks yous. I'd like to first thank our hackathon sponsors, Oracle and Tesuto, and our premium and host sponsors, TechSavvy, our host, Telesis, our connectivity sponsor, Netflix and NTT Communications, our diamond sponsors, Amazon, Imperva, Microsoft, and Oracle are platinum sponsors, and Sixtera, Google, and VeriSign are gold sponsors. If I butchered any names, I'm very sorry. Special thanks to our meeting sponsors. And then a very, very special thank you to you, the members, for supporting us, our board of directors, our sponsors, and a special thank you to Valerie and Day. Without them, this would not happen. There's been some changes. Day Harvey is responsible for making this meeting happen, and she's done a marvelous job. We can all give her a round of applause. And Valerie was an invaluable assistant to the program committee for making all of this happen. So again, applause for Valerie. So did you all enjoy the social last night? Good. A special thank you to Lisa for making that happen. I would also want to thank our contractors, iMiller, Clarity Experiences, Lionspeed Events, Cascadian, and Riverbed for putting all together our technical support, and for the Hamilton Group, Christian Perry, Tessa Overfelt, and Sabrina Hazeltine for helping to put all this together, little background stuff to make everything happen. That said, see you all in San Francisco. Thank you for coming.